Matter and light in our universe were blasted outward by an enormous explosion known as the Big Bang. Well, not exactly. It is true that our universe is thought to have had a truly extraordinary beginning, but before stars, before galaxies, before atoms, and even before light itself existed, the universe entered a phase unlike anything we observe today. During this brief moment, the universe didn't simply expand, it expanded at an unbelievable rate. In less than a trillionth of a second, it grew from something incredibly tiny to astronomically larger. What could possibly drive such an enormous expansion? Well, cosmologists propose that all of space was filled with a quantum field called the inflaton field. The energy stored in this field powered a brief period of exponential expansion known as the cosmic inflation. Wait, then where did matter and radiation come from? Well, for answering that, we need to go over some basics of quantum fields. But don't worry, we won't go deep into the mathematics here. Everything around us, from matter to light, is made of elementary particles, and each particle around us, including electrons, quarks, gluons, photons, and even the famous Higgs bosons, are actually excitations of something called a quantum field. Each particle has its own field, and you can imagine the field as a lake that fills all of space with particles being ripples traveling across it. These quantum fields are always present even if their corresponding particles are absent. So, in the early universe, even before matter and photon existed, their corresponding fields were always present. When the universe began, almost all of this energy was contained in the inflaton field. Just like ordinary particles, quantum fields also have potential energy and kinetic energy. When the inflation began, all of the energy was stored as the potential energy of the inflaton field, and as time went by, it slowly converted to kinetic energy. You can imagine the situation as a ball rolling down a hill into a valley. As the ball descends, its potential energy is slowly converted into kinetic energy. However, when it reaches the bottom, it doesn't stop there. Due to its inertia, it continues moving and climbs up the other side of the valley before coming to a stop and rolling back down. This back and forth motion is called oscillatory motion. In real life, this is usually a damped oscillation because friction causes some of the energy of the ball to be lost as heat and other forms of energy. Eventually, the ball comes to rest at the bottom of the valley, losing all of its energy. So, what happens with quantum fields? Well, we talked about other quantum fields which are always present along with the inflaton field, and all these fields are said to be something known as coupled to each other. This just means that all of these fields were not fully independent from each other's influence. So, unlike an ordinary ball, the inflaton field wasn't slowed by rubbing against the surface. Instead, as it oscillated, it began transferring its energy into other quantum fields. So, during the oscillations of the inflaton field, some of its energy is converted into the excitations of the other fields, and these excitations results in the creation of their respective particles. And thus inflaton field underwent damped oscillations and finally came to a stop when all of its energy was converted into a hot bath of elementary particles. This process is called reheating and is sometimes called the hot Big Bang. Once the inflaton lost most of its energy, it could no longer drive the exponential expansion of our universe, bringing inflation to an end. But why do scientists believe this inflation field ever existed? Well, one of the most strongest reasons is a puzzle known as the horizon problem. When we observe the cosmic microwave background, or CMB, the oldest light we can see on our sky, we find that its temperature is almost perfectly uniform across the entire sky. Even regions on opposite sides of the sky, separated by enormous distances, have nearly identical temperatures. This is surprising because in the standard Big Bang model, without inflation, those distant regions should never have been able to exchange light or any other information. Let me explain. If two systems at different temperatures need to reach the same temperature, or in other words, to be in thermal equilibrium, they need to exchange heat, and this heat is usually done through radiation or photons. So, this means that these two distant points in the CMB were simply too far apart to have reached thermal equilibrium and thus to have the same temperature. But wait, what if the universe started out with exactly the same temperature everywhere? While that's a logical possibility, it is simply an assumption. It doesn't explain why the universe began that way. Inflation offers a much more compelling explanation. It proposes that these regions were once close enough to interact and reach the same temperature before the universe underwent a brief period of extremely rapid expansion, or inflation. That expansion stretched a tiny uniform region into one large enough to become the observable universe we see today, naturally explaining why the CMB is so remarkably uniform. If you are still not convinced, there's another success of the inflation theory. It naturally explains what's known as the flatness problem. The spatial geometry of the universe could, in principle, have been one of three types. It could have been flat, basically the good old Euclidean geometry, where parallel lines never meet, and the sum of the angles of triangle add up to 180 degrees. This we studied in our high school, but that's not the only possibility, as space itself can be curved as is proposed by the Einstein's theory of general relativity. In positively curved universe, parallel lines eventually converge and the angles of a triangle add up to more than 180 degrees. This is actually similar to the surface of a 3D sphere, and this type of universe is called a closed universe. Similarly, it could have been a negative curvature where parallel lines diverge and the angles of a triangle adds up to less than 180 degrees. This type of universe is called the open universe and is comparable to the shape of a saddle. So, which one describes our universe? You might expect the answer to be unknown, but decades of observations from the cosmic microwave background to galaxy surveys tell us something surprising. The observable universe is astonishingly flat. But why does the universe appear so incredibly flat today when it could have been any of the other two geometries? Well, our theory of inflation has an answer to that. Imagine you have a crumpled balloon with scratches and deformities. Now inflate the balloon until it becomes enormous. Even though the scratches might still be there, the balloon has been expanded to such a large size that when you zoom in to the surface of the balloon, it looks flat, even though the global symmetry is spherical or positively curved. Similarly, the universe could have been started with any geometry, but the inflation stretched our universe to such monstrous lengths that looking at our observable part of the universe, it's kind of looking at the zoomed in surface of the inflated balloon. Even if the entire universe was still slightly curved, the portion we can observe, which is the observable universe, would still appear almost perfectly flat. But there's one final question. What happened before the inflation began? Well, actually, we don't know for sure. Some theories suggest inflation may have emerged from an earlier state of the universe, while others argue that answering this question will require a completely new theory of quantum gravity that unifies Einstein's general theory of relativity with quantum mechanics. Whatever the answer turns out to be, it's one of the greatest unsolved problems in science. And maybe we'll explore these ideas in another video. So if you'd like to see that, consider subscribing. Thanks for watching.